So in section 1.1, we're going to get familiar with the absolute value function. So we have y equals the absolute value of x, and we want to find out what does it look like and what are some of its characteristics, and then we're going to use transformations to graph other absolute value functions. So this is the main parent graph is what we call it. And what I'm going to start out by doing is just finding some solutions or some xy coordinate pairs that are solutions to our equation or our function up here. So the way we do that is usually just by picking x values. So I'm going to pick a couple. Let's put -2 in for x and figure out what y would have to be. So y is equal to the absolute value of -2. Well, that means y is just equal to 2, right? So when I put in -2, I get 2 back out. Let's just try those numbers. If we need more, we can do it after that. If I plug in -1, we'd have y equals the absolute value of -1. That's just 1. So when x is -1, y has to be 1. If I put in 0, right, when x is 0, y has to equal 0. If I put in 1, I'm going to get 1. 2, I have to get 2. Well, let's plot those points and see what it looks like, and we'll decide after that if we need some more or not. So I've got a point at -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. If I plug 3 in, right, the absolute value of 3 is 3, so x and y. If I plug in -3, the absolute value of -3 is also 3. And we could keep going, but we can see what's happening here. This right side is just linear. It's headed up that direction. And my left side is also linear, and it's just headed out that direction. So this is what the absolute value function looks like. Okay, what I'd like you to do is I want you to pause the video, and I want you to write down just 3 characteristics of this function. Like, what are 3 things that make this function unique or different from other functions, from the graphs of other functions? So go ahead and pause and do that, then we'll come back together and I'll talk about some of those characteristics. So a couple things, hopefully you notice. One is it has that V shape. And all absolute value functions have those V shapes. Another one is, if you look, it's symmetric. Right? If you picture just a line, a vertical line kind of going down the middle there, if I were to fold it a half across the y-axis there, it would be symmetric about the y-axis. It has this point right here where it changes directions, right? It goes from negative slope, if you can see my cursor there, to positive slope. Go ahead and label that. We refer to that as being the vertex of the absolute value function. So it has a vertex. Maybe you noticed that it's, the entire graph is above the x-axis. It touches, I guess, at 0, 0, but then everything else is above. So really quick, you've done this last year, but let me just remind you. Let's find the domain of the graph and the range of the graph. Okay, so if you remember with domain, it's what can x be? So as I go left and right, sometimes what I like to do is if you just picture like a vertical line. Let me see if I can just get a vertical line up here. So if you picture a vertical line, so here's my vertical line. If you get it, and you just picture like running it across here, so if you can watch that go across, you want to know left and right, how far does the graph go? So if I start on the left side, right, it's going to go forever to the left, and as I go to the right, it's going to go forever to the right. So what that really means is that x can be anything. The way you write that with interval notation is it looks like this. We do a bracket. Let me just switch back to my marker here. So we do a bracket, and it starts at -infinity, and it goes to positive infinity. Well, and you know what? With infinity signs, we always do rounded. I apologize. I should not have done a square bracket. Now for the range are the y values. You remember that from last year. So with the y values, you always start from the. You're always going to start from the bottom and go up. So here's my horizontal line. And if you're just picturing that, oops, sorry about that. If you're just picturing what's happening here, I select that horizontal line, if it will let me here. And we're going to go from the bottom up. So as that vertical line goes up, you always start from the negative to the positive side. Like with the X, we went from the negative to the positive side. We're going to do the same thing here. So we're going to go from the negative to the positive side. And right now, it's not wanting to cooperate with me. But if I draw a vertical line as I go up, I'm going to get to right there. Like right there is where I'm going to hit the graph. So that means my graph is starting at 0 on the y-axis. And then that graph just keeps going up, right? As I go up, this graph, it's still going up as I get up there. So my range is going to go from 0, and I do a square bracket because it actually touches at 0. That's what the square bracket means, is it includes that point. And then it keeps going up forever, so it goes to infinity. So hopefully you remember that previously, what you've learned. But domain is left and right. So start from the left side and go to the right side. And how much of the x-axis does the graph cover? For the range, you go from the bottom up. Again, how much of it does it cover? Okay, so that's some of the characteristics. You know the domain and range. You know it's V-shaped. You know it's symmetric. It has that vertex. Now, this whole thing together is called, again, we could say this is the parent graph of the function. So write that above your graph right there. Put down parent graph. And what we mean by that is that it's the original. And then from there, we're going to figure out how do we do transformations with that graph. So how do we shift it up or down or left and right? We can actually make it steeper or less steep. And so we're going to go through all of that. Okay, we're going to look now. So these are our learning goals right here, right? I can graph the absolute value function using a parent graph and transformations, and we haven't done that yet. We've done the parent graph itself, but we haven't done transformations. We're going to. And then I can find the domain and range of the absolute value graphs. And so we just found the domain and range of that last graph. We'll keep practicing that. Okay, so let's go ahead and figure out some of these transformations. So if you look at these next two examples, we're going to do the same thing we just did. We're going to make this really quick. We're going to make a table for each of these and then use the table to graph the function. And what we want to do is we want to compare that to the original parent graph that we graphed up above. Okay, so let's start with this first one. I'm going to actually have you do this on your own. So if you would pause the video, I want you to make a table, plug in some x values, and find some y values that go with those x values. And then we'll come back together and graph this and see if we can figure out the transformation. So the points I used is I used the same ones as up above. I went from -1 to +1. And when you plug that in, you plug in -2. The absolute value of -2 is 2, and 2 plus 3 is 5. So when x is -2, y has to be 5. You put in -1, and y has to be 4. You put 0 in, and y has to be 3. And you may not have done those same points, and that's fine. But we ought to end up with the same graph. So it looks like this. So -1, 4, 0, 3, 1, 4, 2, 5. Now, if we take that now, we want to compare that to this original parent graph. So just a quick reminder of what it looked like. Right? It had a vertex at 0, 0. They went over 1, up 1, over 2, up 2. So this one down here was that y equals, or f of x equals, the absolute value of x. The black one's our new graph. Pause the video for a second and just write a quick statement saying how is the new graph, the absolute value of x plus 3, different from the original graph, the parent graph, the absolute value of x. Okay, hopefully you just said, yeah, it's just shifted up 3. So that should tell us something. When I added 3 on the outside, it just took the graph and shifted it up 3. It turns out, and we can probably guess this now, like if I were to subtract 2 from the outside, let's actually do that in a different color. If I were to subtract 2 from the outside, all that would do is take the graph, the exact same graph, and shift it down 2. So that outside number, either subtracting or adding, it does not change the shape of the graph, it just translates it, which means it just moves it. Okay, let's try this next one. So same thing. I want you to make a table off to the side, plug in some values, and let's sketch the graph of it and compare it to the original parent graph. Now notice this one has the -2 on the inside of the absolute values. So that's going to change it just a bit. So go ahead and pause it, find a table, graph it. if you use those same points, what you'll find that happens, right? If I plug in -2 minus 2 is a -4, the absolute value is a +4. If I plug in -1 minus 2 is a -3, the absolute value is a +3. If I put in 0, I get 2. If I put in 1, I get 1. If I put in 2, I get 0. So if I plot those points, it's looking like this. -1, 3, 0, 2, 1, 1, 2, 0. Well, the issue with this is I know it has to be a V shape because it's absolute value, so I can't see where the vertex is. I'm going to keep going. Let's plug in 3, maybe 3 and 4 and see what happens. If I plug in 3, 3 minus 2 is 1. The absolute value of 1 is 1. If I plug in 4, 4 minus 2 is 2. Okay, now I can see that V shape. So this is what y equals the absolute value of x minus 2, or m of x equals the absolute value of x minus 2 looks like. Okay, again, I want you to compare it to the parent graph, which I'll do in red again. Right, it looked like this. That was our original one. That's the absolute value of x. So pause the video, just take a second and explain how that graph is different. Okay, what we should have seen, right, is that it is shifted right 2 units. So interesting enough, when it was on the outside, the +3 and the -2 over here, it shifted it up and down vertically. When it was inside with the x, it shifted it horizontally. Now the tricky part is this was a -2, but it shifted it right 2. So we could probably guess, and this is true, if I have y equals the absolute value of x plus 3, right, a +3, because we're going to go actually the opposite direction. So again, let's do that a different color. We'll do that blue again. So if I have the absolute value of x plus 3, it's actually going to take the graph and shift it left 3. So it's going to look like this. So if it's inside of the absolute values, if it's inside with the x, it shifts it left and right. But in the opposite direction, we would think. If it's plus, it goes left. If it's minus, it goes right. Okay, those are our first couple transformations. Here's another one. Let's come down here. We're going to, well, really quick, here's a couple of examples. I don't even want you to graph these. Just pause the video for a second and you decide on number 1 and 2. What's going to happen to those? What kind of transformations is going to happen there? How are they going to be different from that original graph? So if you look at the first one, the -1 is on the outside. That means it moves it vertically, and it's a -1, so it's just going to take the graph and shift it down 1. That's how it's going to be different from that y equals f of x. And number 2, n of x equals x plus 4. The plus 4 is on the inside. If it's with the x, it goes the opposite way. So if it's a plus 4, it's actually going to shift it left 4. It's going to shift it left 4 from that original graph. So outside moves it up and down, inside moves it left and right. Just remember, if it's on the inside, you go the opposite direction. Okay, here's our next one. So you want to know what happens when, instead of adding or subtracting, what if I multiply? So I want to graph y equals 2 times the absolute value of x. So again, we're just going to make a table, just like we had before. So make a table. I'm going to use those same values, at least as a starting point. If we need to do more, we can. So if I plug in -2, the absolute value, we end up with this, right? Q of -2. I go 2 times the absolute value of -2. Well, the absolute value of -2 is 2, and 2 times 2 is 4. If I plug in -1, the absolute value of -1 is 1, and 1 times 2 is 2. If I plug in 0, absolute value of 0, 0, 0 times 2 is 0. If I plug in 1, I get 2, and I plug 2, and I get 4. So, okay, let's plot those points. So I've got -2, 4, -1, 2, 0, 0, 1, 2, 2, 4. And we know it's a V shape, so I think we've got a pretty good idea of what it looks like. Okay, let's compare that to the original graph. I'll do it in red again. So remember, the original graph, the vertex is in the same spot, but it went over 1, up 1, and then over 2, up 2. So it looks something like this. Oops, let me keep that going. So if we want to describe like how did this graph change from the original parent graph, which I have in red right there? What would we say? It's steeper. The exact terminology is actually this. I want you to write this down. Is we say it is a vertical stretch. So what you're saying is you're taking the graph, and if you picture grabbing the top of the graph and just stretching it up, like it's going to make it steeper. So a vertical stretch. Well, it turns out, think of the parent graph. Right, this is my parent graph. If there's nothing in front of it, it really has a 1 there. It's 1 times the absolute value of x. Well, if I multiply it by a bigger number bigger than 1, all it does is multiply all these y coordinates by that number. So this was negative 1, 1. Now I times my y coordinate by 2, right? Because there's a 2 in front. So I end up with 2, and it was a 2, so now it's a 4. So all you do is times all the y coordinates by that number, which makes it steeper. If I were to do this, then y equals a half times the absolute value of x. Now you're going to times all your y coordinates by a half. So if I were to do that, it's going to end up looking like this. 1/2 the absolute value of x. Instead of going over 1 and up 1, it's going to go over 1 and up a half. And instead of going over 2 and up, instead of going over 2 up 2, it's going to go over 2 and up halfway, which would be 1. So it just cuts all those y values in half. So it ends up looking like that blue graph right there. What we call that is a vertical, that's a vertical, the book calls it a shrink. Sometimes you'll see a compression. I don't care how you refer to it, but in your book it will use that word shrink. So what it really means is you're kind of like squashing taking that red the red parent graph, and you're squishing it vertically. It's going to go up slower. It's going to be less steep. Hey, the last one is a negative, and just for the sake of time, I'm going to go kind of quick through this. If you have a negative 1/2 in front, that means I take the original y values and I times them by a negative 1/2. Well, what that's going to do to the graph, we'll pick even a different color, is instead of going over 1 up a half, I'm going to go over 1 down a half because I'm timesing by a negative 1/2. So the half does the same thing. It's still a vertical shrink. But if there's a negative in front, it reflects it across the x-axis. So now it's opening down instead of opening up. So that's a summary of all the different kinds of transformations. And now we're just going to practice with those. So really quick, pause the video, see if you've got this. Just in your mind, I want you to come up with a description of like what happens, what kind of transformation is this? What is that -3 doing? How is that different from the original parent graph? What is that 1/4 doing? So pause the video, come up with what you think, and then we'll unpause it, and I'll let you know what they do, and you can compare your answer. So a -3 is going to do two things. It's going to make it open down because it's negative, and it's going to the 3 is going to do a stretch. So normally on that function, right, the parent graph, I go vertex over 1 up 1. This is what the original graph looks like, right? So what happens with the -3 is we times all those y coordinates by a -3. So I go over 1. Instead of going up 1, I go down 3. So it's down here. So what that's going to do is it's going to make it steeper. It's going to be a stretch, but the negative is also going to reflect it down. The 1/4 now, right, that is going to be a vertical compression because that number is less than 1. So I times all my y coordinates by a number less than 1. So instead of going over 1 and up 1, I'm going to go over 1 and up 1/4. Instead of going over 2 and up 2, I'm going to go over 1 and over 2 and up 1/2 because that's 1/4 times 2. So that's going to be a compression or a shrink. So we'd say, what's the transformation? It's a vertical shrink. Okay, so let's kind of summarize all this. Actually, what I want you to do first is I have a little app here on Desmos. So if you go online and you type in this www.desmos.com/calculator, then it has this code right here. It will take you to a function that looks like this, where you can change A, H, and K, and you can see what happens to the graph. So if you actually want to pause this video, go get onto that website and see what happens, then we'll come back and summarize it. Okay, what you should have seen is H, like we saw in those examples we did with our table, H is a horizontal transformation, so it moves the graph either left or right. The tricky part is if there's a plus on the inside, it actually moves it left. It goes the opposite way. And if there's a minus, it goes right. The K is also a translation, but instead of being horizontal, it's vertical. So it moves the graph either up or down, and really straightforward, plus up, minus down. The last one is that A, the number out in front. Okay, that can it can be a vertical stretch, so a vertical stretch, which means makes it steeper, or it can be a vertical shrink, which makes it less steep. And this is how you tell if the absolute value of A is less than 1. Ooh, I did that backwards, I'm sorry. Let me fix that. So if the absolute value of A is greater than 1, it makes it steeper, it stretches it. If the absolute value of A is less than 1, then it shrinks it. The reason why we put the absolute value is because it doesn't matter if I have y equals 2 absolute value of x or y equals a negative 2 absolute value of x. It doesn't matter if A is positive or negative. If you take the absolute value, which is 2 in both cases there, it's going to make it steeper. It's going to stretch it. The difference is this one's going to be stretch and opening up. So it's going to be steeper and opening up. This one, because of the negative, is still going to be steeper. It's still going to be stretched, but it's going to be opening down instead. Okay, go in that direction. The other thing A does is A reflects it vertically. If it's negative, sorry. Reflects vertically. I'm struggling here, sorry. Reflects vertically if negative. So, right, so if it's negative 2, it's still going to stretch it, but it's going to be opening down that direction. Okay, let's just do a couple practices real fast. I know this video is going kind of long, but let's do a couple practices really fast to make sure we get it. So if I ask you to graph this, y is equal to, I got y is equal to absolute value of x minus 2 plus 1. Okay, and we want to sketch a graph of this, and let's find the domain and range. So here's my x and y axis. Okay, there's a minus 2 on the inside. If it's inside, that moves it left or right. And remember, we got to go the opposite way. So if it's a minus 2, I'm going to shift right 2. So now the vertex is no longer at the center. The plus 1 on the outside is going to shift it up 1. So I've got to go right 2 and up 1. That's for my vertexes. Nothing else has changed. In fact, if you want to look and see what A is this number out in front. There's nothing there. So it's like having a 1 out there. So positive 1 means it's going up. So we're going to go left 1 and up 1. And right 1 and up 1, just like the normal parent graph. There's my graph right there. Hey, domain and range. Domain is pretty easy on this. Domain is what can x be. So going left and right, how far does the graph go? Well, with this V shape, the graph is always going to go from negative infinity to infinity. The range is different because the range is the y value. So if you picture a vertical line running up, it's going to hit the graph right here, right across there. At that point, that line's going to hit that graph. Look on the y-axis over here. That's when, right over here, that's when y is 1 right there. Okay, that's when it's going to hit the graph. So I'm going to say it starts at 1, and then how far up does it go? Well, it keeps going up forever, so it goes to infinity. So my domain is basically everything. You can, by the way, you can put all real numbers like that because the domain goes from negative infinity to infinity. And the range goes from 1 to infinity, which we could also say y is greater than or equal to 1 if you wanted to on there. Let's try another one. So this is the way I'm going to write it, right? Interval notation right here. But you could also write it this way, like that works. Here's another example. Let's do one more. I got 2 more here. Okay, so this first one, I've got a plus 3 on the inside. I'd always find your vertex first. That's going to shift your vertex left 3. There's nothing on the outside, so that's where my vertex is. A is a negative 1, right there. So instead of opening up, it's got to open down, but there is no stretch. It's just the normal one. So you go over 1, down 1, over 1, down 1. That's what my graph looks like. Let's do the domain and range with that. So domain never changes. It goes forever left and right. It's negative infinity to infinity. The range, if I start from the bottom, like if I start down here and say, where does my graph start down here? Well, the graph goes down forever. So it starts at negative infinity, but it doesn't go up forever. It ends right here. So if I'm looking on the y-axis, look at what it is on the y-axis. That's right here. That's when y is 0. And it actually hits there, so it looked like that. There's my domain and range. Let's do this next one. Y equals 2 times the absolute value of x minus 3. So find your vertex. There's nothing on the inside, so it's not shifting left and right, but I do have a minus 3 on the outside. That's where my vertex is. There's a positive 2 in front. Positive means it's opening up, and it's going to be a stretch because there's a 2 there. Normally I'd go over 1, up 1, but I'm timesing that y distance by 2. So I go over 1 and up 2. Over 1 and up 2. So it's going to be steeper. So it's shifted down 3, but there's also a vertical stretch. Let's do domain and range. Domain never changes. It goes forever left and right. The range, though, if you run up that graph, if you see my cursor right there, the graph does not start until I get to right there. That's when y is negative 3. Then the graph keeps going up, and it's going to keep going up forever, so it goes to infinity. Now, sometimes you might see again in your book, it may just write out all real numbers, right, for the domain. All real numbers means x can be anything. And then for the range, the way you'd write that is y is, it's all the numbers bigger than negative 3. So y is greater than or equal to negative 3. They could write it that way. So you could see it written that way. I like interval notation. That's the way we're usually going to do it in class, but sometimes the book does use that. Use those inequality symbols instead. Okay, sorry this video went a bit long, but hopefully that helps. So again, our goal was that we can graph absolute values functions using transformations. So we're not using tables anymore. We're just starting with the parent graph, the original, and we're using transformations to graph it. And the second thing is being able to find domain and range, which you guys have done before, but hopefully that was a good reminder on it. Anyway, thank you.